correspondence for quantum torus.
For quantum torus, thank you, yeah. Yeah, so my talk will be, as a change from Sergei talk, will be completely mathematical, but at the end you'll see it has some relation with, eventually, with what he'll talk maybe after. Yeah, but so what is a quantum torus? Yeah, so this is something for me not to forget what I want to tell. Yeah, just ignore it a bit. It's a small plan. What is quantum torus? Yeah, it's not a space, it's algebra, not AQ. Q is a complex number, and I will assume that Q is not a root of 1. Although in principle, these things can be weakened. One consider maybe Q is not just equal to 0. It's, in some sense, can be generalized. And mostly, I will assume that Q is norm less than 1. So what is the algebra AQ? It's algebra with two generators, x hat, y hat. Modular relations are both invertible. It's not relation, just that kind of inverse things. And also you write relation like this. Yeah, so the basis of this algebra is, obviously, of this algebra is a set of all monomials. It's like functions on usual torus. It's quantization of algebra functions on usual torus. And now I want to speak about holonomic modules. This algebra has a filtration, kind of, it's called Bernstein type filtration. It actually has many filtrations, but I'll take this kind of AQ less than N is this kind of span of xi by j, where I and let's say j was less than N. Or we can put I plus j, it gives kind of the same picture. And then I'm ready to give an important, the main definition, where it's kind of standard in this game. What is a holonomic module? M is holonomic if it's finitely generated. And let's choose space of generators. G will be generators, subset of generators of finite dimension. And then condition of holonomicity means that dimension of kind of corresponding filtration of my module is capital of N. No. It grows linearly. In fact, it cannot grow less than linearly, so it doesn't depend on choice of generators. We immediately follows from the definition. Yeah, and N, in fact, is N to power 1. And 1 is 1/2 of number of generators. So one can imagine how generators things with several variables. 1 is 1/2 of number of generators. Yeah, so that's definition completely parallel to what one can do for modules of polynomial differential operators on a vector space. Also introduce Bernstein filtration and repeat the definition. Now I will draw some parallel with usual differential operators on a curve. So I'll just draw a big line. And so I will fill eventually this disk by analogy. Here it will be differential operators. Again, and here it will be Q difference operators. For differential operators and Q difference operators here, just repeat, I have this algebra C of, maybe I'll just draw first classical limit. It will be Poisson algebra. In differential operators, the classic, symplectic manifold will be cotangent bundle to a curve. And if its curve is a affine line over complex numbers, then we get C cross C, let's say coordinates x and y, and to form which will be dx wedge dy. Okay. And here my classical manifold is C star cross C star with coordinates x and y, and to form dx over x, which dy over y, kind of logarithmic version of usual differential operators. Now, corresponding kind of non-commutative algebra. Here it's we consider C of x and maybe d over dx, where d over dx is the derivation. It's x by derivation. So we consider twisted, so this will be polynomial some variable which is not commuting but satisfies this commutation rule. And modules, one can interpret it whatever, like quasi-coherent sheaves on the line, because they're not necessarily finitely generated as modulus over x. Sheaves over a fine line with vector coordinate x, plus connection. This derivation gives a connection. And in a kind of quantum case, my algebra is AQ, which maybe I just write it something like in a similar way. X hat, y hat inverse. We have y hat acts by, now not derivation, by automorphism, by rescaling q hat, x hat. This y hat acts by automorphism of this algebra. We can consider these polynomials and modules. One can see as it's the same as quasi-coherent sheaves. Sheaves over now C star, this coordinate x. And instead of connection, you get equivariance when you get group q to power multiplication variable by q to power z. It should be equivariant with respect to this section instead of connection. Okay, so that's pretty simple. Now, in my first talk several days ago, if you still remember, I started with formal classification. If I have, let's say, I want to describe holonomic modules in some different terms. That's the Riemann-Hilbert correspondence. And for differential operators, first I start with formal classification. So it means that I consider, instead of this ring, I consider Laurent power series ring in X, d over dx, and still polynomials in d over dx. And I consider modules which are come from coherent modules. And because this is a field, it will be finite dimensional vector spaces with connection, kind of meromorphic, formal meromorphic connections. And here the story was, what I explained to you, that this category of holonomic modules over this ring is a direct sum over certain blocks. And blocks correspond to irregular terms, what's called irregular terms, which we thought as kind of certain series, set of series finite expressions C maybe AIBI times x to AIBI. AIBI belongs to negative or maybe negative rational numbers, so it gets expressions with poles, and mod out by Galois group action. So x AIBI goes to x 2p pi square root of minus 1 AI E2 divide by appropriate the section of Galois group, which has finite orbits, and there was a geometric meaning. What are this? One can see it's algebraic. One can say consider all such expression model the section of the hat action. But there's also geometric meaning, which was the following. Namely, you consider what? You consider germ of you consider surface I think variables are here something like coordinates x and y over x, like this. Maybe y. Oh, y times x. Sorry. You consider a plane with coordinates x and xy, and with this and put this to form. Then this to form will have pole of order 1 along vertical line and pole order 2 at infinity when you compactify these things to infinity. You consider formal disk times p1. It will be p1 vertical direction and formal disk in horizontal direction. So we get these things, and now we start to make. It has one divisors of and it has pole of order 1. And then we start to make kind of blow-ups, and somewhere we get divisors, other divisors with poles of order 1. This corresponds to all interesting irregular terms. This corresponds to regular singularity, and the rest correspond to irregular term. It's kind of, one guy was regular, and this is irregular terms. And here, also one can, and I explained you that this, to obtain this formal classification, this level 2 routine theorem, it's really easy. You first kind of try to think about curves passing through the things and how you make blow-ups eventually that it meets divisors only when you have first order pole. And the same procedure can be applied to D modules. To regular, you can see, make kind of blow-ups for non-commutative scheme and do the same story. And now in this case of formal Q-difference operators, what happens is this also have formal classification. Now I consider C of, again, the same thing over X. And now of this variable, X is a hat, maybe Y plus minus 1 is Q difference, Y hat. I put Y hat here. I consider Q difference operators over the Lorentz series in non-variable, and then holonomic modules. The category of holonomic modules of the things will be direct sum of blocks. And blocks are much simpler. Blocks correspond to rational numbers. Yeah, so there's no continuous parameter whatsoever here, just analog of a regular type. It's just a rational number. If it's 0, it's analog of regular singularity. And what is the geometric picture here? We again do the same story. We have coordinate x now and y vertical. Again, it will be product of P1 and formal disk. But now my volume form has poles of order 1 at all 3 divisors. This is small. This I will not use. But now if I make a kind of blow-ups, I start to make blow-ups only making whatever it's called Fourier fractions. I get rational, I get blow-ups here and here, and always I get divisors as order 1, just on the first step. And all trees, which how I make these divisors, correspond to positive rational numbers. This is 0 and negative rational numbers. So I get Q, which is, there are 3 types of divisors. This is kind of regular kind situation. And these are 2 types of irregular, in this case. Yeah, so it's a completely parallel story. And what is interesting here, that each block, let's kind of jump back and forth. So we have this decomposition of direct sum of blocks. So there will be different modules which do not talk to each other, and one can only study subcategory for each block. And as I explained here, this category of each blocks was equivalent to the following. We consider, if you kind of literally do these D modules and try to see, all blocks will be isomorphic to each other. In this case, each block is the following. If you consider quasi-coherent shifts on C, which is a affine line, and a affine line will be this each minus 1 divisor. Each minus 1 divisor is isomorphic to a affine line here. It's kind of residue of eigenvalue of whatever Higgs field, if you think in semi-classical terms. Yeah, so each block is quasi-coherent shifts of a affine line, which are Z equivariant. Whatever lambda goes to Z plus lambda equivariant, with some coordinate lambda. And such that you get only finitely many, if you kind of mod out by Z, you get finitely many pieces and finiteness after division by Z. And by kind of transcendental means using exponential method, the same as coherent shifts on C star with finite support. And yeah, so it's just, it's the same as finite dimensional representation, invertible operator in finite dimensional space. Or maybe you can write it C of exponent plus minus 2 pi I lambda modules. And this can be thought it's kind of some monodromia of your, in some formal sense, of the equation. What happens with this story? It's exactly parallel. So each minus 1 divisor is not A1, but A1 minus 0. Now it's kind of C star. It's a multiplicative situation, and each block corresponding to this minus 1 divisor is the same as quasi-coherent shifts over C star, which I don't know, it's maybe its coordinates, let's say, whatever, mu. And mu goes to, and equivariant under mu goes to exponent of Q to power Z mu equivariant. And finite after the same story, and the same, you get the same as constructible shifts, coherent shifts with finite support. Support on what? Over kind of, maybe I just go to play now important game. Now with right, it's big EQ, which is C star over Q to power Z. It's elliptic curve, so it's for Q less than 1. Now it starts to play roles at Q less than 1. It's elliptic curve. Yeah, so it's after factorization, if you kind of divide your C star by orbits of Q, the fundamental domain will be annulus, and you glue both ends, you get torus. Yeah, so that's by division of C star by this geometric progression, you get a torus, you get elliptic curve. And Here we don't have this description because it's not a fine variety. We say that it's finite dimensional module of some algebra. It's not finite dimensional algebras. It's coherent sheaf with finite support. And coherent sheaf with finite support is very easy. Just bunch of points, maybe with multiplicities. So one can see what, for example, the indecomposable object will be a point on the thing with certain multiplicity. Yeah, so we get this simple formal classification. And now I want to say something about elliptic curve, which plays absolutely fundamental role here. It's about Fourier-Mukai transforms and semi-stable bundles and all these things. Yeah, so it was, if you consider on elliptic curve, one can, so that's one of very early papers by Michael Atiyah, when he, probably at that time he didn't know what, will he become analyst, topologist. It was paper in algebraic geometry, yeah. Yeah, so it's very early result of Michael Atiyah. It's classification of indecomposable let's say coherent sheaves on elliptic curves. Any elliptic curve. If you consider coherent sheaf, whatever E, no, maybe just denote by some other letter F, coherent sheaf on elliptic curve. Yeah, it's a very nice thing because it's indecomposable, and any coherent sheaf will be finite direct sum indecomposables in a unique way. So you kind of we know explicitly the whole category. And the story goes like this: if you have coherent sheaf, it has two invariants. It has a degree, which is kind of integral first chain class over curve. Sorry, let me just truly notation curve E, which is an integer, and you have a rank at generic point. It could be torsion sheaf and so on. So it's in Z greater than 0. Yeah. Now you put these two numbers in a complex plane. There's what's called Bridgeland stability conditions. At that time, there's no such terminology. There's no Bridgeland, I think. Yeah, Bridgeland definitely wasn't born. Yeah, so Z of F will be complex number, which is minus rank plus square root of 1 minus degree plus square root of 1 times rank. And yeah, so if you try to see kind of non-trivial objects, if rank is equal to 0, that means it's torsion sheaf. So it means that it's some of kind of coherent skyscraper sheaf with multiplicities. It's if torsion, then I get some point in elliptic curve, and I consider it has some ideal in local ring, and I consider O of x0 divided by some power of thing, m greater than 1, will be the length of this module. It's like generalization of Jordan block. This is typical indecomposable torsion sheaf. Yeah, so you can, it's first chain class. Its degree of this guy is equal to m, and minus degree is negative number, so you should put it -1, -3. This will be torsion sheaves, indecomposable sheaves. This will be length. No, but then you can have something in kind of rank 1. Yeah, Yeah, consider shifts of rank 1 in given degree, for example, degree 0 will correspond exactly to points of your elliptic curve if you choose 0 in your elliptic curve. So it will be you get such object and so on. And what is remarkable, if you consider what are parameters of indecomposable object, what the theorem says the following. For any degree and rank, which belongs to this, maybe belonging to this blue domain, where degrees belonging to domain when degree is strictly positive, rank equal to 0, or degree is arbitrary and rank is strictly positive. This blue domain. Moduli space of this indecomposable objects is our elliptic curve itself. Yeah, for example, for torsion, it's a point where we put this max power divided by ideal. Here, consider what line bundle we put on a curve and multiply by or twist by some ample bundle. And the remarkable thing is also goes for bundles of rank 2, 3, and so on. They're all parameterized by elliptic curve. So it means that indecomposable objects are in one-to-one correspondence with what? You consider elliptic curve and multiply by z square minus 0 and maybe divide by plus minus 1 to get unique representative in this blue domain. Yeah, that is yeah. So that's one can make explicit construction of this vector bundles of higher rank, which are indecomposable, and in fact, the story is the following. It can be easily defined these days as the following dates. It's some kind of universal covering of SL to Z, or pull back in universal covering of SL to R, acts on bounded derived category of coherent shifts of the elliptic curve. And what is the action? You get some, for example, you can multiply by line bundle, which I can say something like or 0 on E. What does it mean? I have any point, it is a divisor. I can see the sheaf of functions which can allow have poles at kind of origin for the group law. I get this line bundle, and also I get Fourier-Mukai transform. Fourier-Mukai, because dual to elliptic curve is elliptic curve. On elliptic curve, we get universal bundle. And then one can use this pull back and push forward construction to make automorphism of category. You calculate what happens on K0. You get some matrices in SL2Z, so you can see that how it associates to these functors matrices. This matrices generate the whole group, and also maybe add shift operator. And then you can go from torsion shifts to kind of any non-primitive vector. Any vector is multiple of primitive vector. So you can move by the group to, let's say, horizontal line. So it's easily obtained by Fourier-Mukai transform from torsion shifts. Yeah, so that's the whole story. And yeah, so you get these blocks will be exactly these categories. They're all equivalent to each other by Fourier-Mukai transforms. Yeah, so we get a pretty satisfactory picture for formal classification. I think it was I remember many years ago, there was a paper by Ginsburg and Baranowski. I think they classified our formal power series, or they describe the category of formal power series maybe with slope zero kind of analog of regular part. From my perspective, it will be torsion shift. From this perspective, it could be first maybe kind of torsion shifts on elliptic curve. But if you apply Fourier transform, you get semi-stable By the way, these indecomposable objects are semi-stable with given slope. So one can associate with semi-stable with of degree 0. Yeah, so that's pretty clear picture here. And now what to do with how to go from non-formal classification to meromorphic classification. So meromorphic classification, again, one can build some parallels with what does mean meromorphic classification. Now we, instead of formal power series, we consider germs of meromorphic functions. It's germs of analytic functions and a lot of finite order poles. Yeah, so we get this thing instead of formal series without convergence condition. I recall that in the case of differential operator case, what we have is the following. We have kind of Stokes phenomenon, yeah? We have Stokes phenomena. And namely, if you consider a differential equation puncture disk in a small sector, in any sector can be in small sector, it's equivalent to normal form in which you obtain from formal classification. Sum to normal form from formal classification. And then you get this identification is not really canonical. It gives you only a flag because you consider solutions which go very fast, then less fast, and so on. You get flag by growth. And then there was a kind of complicated picture because if you change direction, the order of how formal solution grow will change. So you get modification of flags. And then I draw you this, if you remember, this kind of complicated picture. And there was some equivalence with categories of constructible shifts with macro-local support and vanishing at 0. You get kind of shifts with constructible shifts. With macro-local support sitting in a kind of 0 section. First I should add, plus a union of this positive conormal bundle to my curves, which correspond to terms in irregular terms in formal classification. But also I should remove kind of this middle part is removed. There's no shift with 0 inside. It was kind of pretty ugly. Inner domain in 0 section. Yeah, so it was pretty complicated story here. Because filtrations, when consider formal different normal parts of formal classification, in different sectors they have different growth and things jumps. But fortunately, in the skew difference case, there's no such trouble. One can the growth doesn't depend on, there's no dependence on the sector. You don't have to divide your elliptic curve, say, on some domains. And there is a classification theorem by Ramis and Zhang. it's not very old. It's pretty recent result. Which gives analytic, again, meromorphic classification. And the classification is the following. This modules over AQ modules, AQ kind of meromorphic at 0. Consider this germs modules. They give a vector, first of all, they give a holomorphic vector bundles. Over elliptic curve EQ, or plus some additional data. Why it gives holomorphic vector bundle? It's actually obvious, because if you have on this, maybe it's different story. If you have my disk and let's say maybe smaller disk and get holomorphic, we get a meromorphic vector bundle equivalent with respect to dilations, then we can forget about meromorphic structure, consider this as holomorphic on punctured disk, and just identify the full fibers, get a holomorphic bundle on a Q. And now there's analog of things and endowed plus filtration by rational numbers, because exactly it will be, all solutions should grow like, maybe just let me explain what goes on. Yeah, if, for example, consider equation something like this. F of Qx is equal x to power AB, maybe multi-valued, maybe rational number, phi of x. Yeah, you write this kind of rank 1 bundle. You translate from one point to another and should multiply by some invertible function. And if you write these things, and if you write what is f of q and x, will be x to power AB times qx to power B, also times qn minus 1 x to power AB times phi of x. And here you see that you kind of x is fixed. Maybe put some point x0. You consider some go to the orbit, and then you see that fx0 is fixed, but n goes to infinity. And approach point 0, then the solution will grow like u to power n square over 2 times AB plus maybe O of n. This will be the growth of my solution. At point q to power n, maybe I put absolute value of q. Yeah, so you see that it's the growth parameterized by this rational number a over b, which you put into the game, and you get a filtration. You consider point on this vector bundle, move it by parallel, kind of by action of equivariance to fiber closer and closer to 0, and see what will be the growth of the norm. It will be growing like some rational n square over 2 times some rational number. And then you get a filtration. It will be filtration by holomorphic subbundles. And associated gradient will be semi-stable, which will mean direct sum of this indecomposable. Semi-stable with slope lambda. With slope AB. This corresponding slope, which is a rational number. So you don't see here torsion shifts. You only see kind of, you don't see torsion shifts. You see only vector bundles in this case. This filtration, actually it's really funny filtration. The story is the following. I wrote you this picture, and in fact, this old theorem of Atiyah, it's kind of illustration to notion of regional stability, or it's classical stability, that any coherent sheaf admits a unique filtration. In this case, it's for case of elliptic curve, it's kind of completely obvious because it that decomposition of indecomposable summons, but it's not canonical. So what's canonical is filtration. Such that associated gradient are semi-stable, and this filtration by rational numbers, associated gradient are semi-stable, and this is called Harder-Racine filtration. So it's pretty general. It can be done for any curve, not for elliptic curve, but curve for arbitrary genus. You get on coherent shifts, you get canonical Harder-Racine filtration. Again, by degree and rank, the same picture. And this is filtration by rational numbers, and quotients are semi-stable. Here we get filtration by rational numbers, and quotients are semi-stable. But it is, the difference, it's a different filtration. Here filtered to kind of increasing order, and here filtered in decreasing order. So it's anti-Harder-Racine filtration. It's kind of anti-H infiltration. It's something not canonical. It's extra things which you could vary for a given bundle. Kind of try to. So you get the description. It's a coherent shift with anti-Harder-Racine filtration. But also, there's no torsion into the game. And now I'm almost will be. Yeah, you see that it's something a bit unsatisfactory in this picture. We miss torsion. Yeah, we have we consider things with anti-Harder-Racine filtration, but there's no torsion in the game. And here there was also something a bit untidy. We consider constructible shifts with some microlocal support, but it was vanishing. There's no contribution like for delta function here. It's completely parallel picture, and the whole story, it's kind of became much nicer if you do global classification. Actually, it's not totally trivial. It reduces from local one. Suppose you get a M is a module, AQ module, which is holonomic. Now we consider it is as module over just first generator. Yeah, so it's in general, it's not a finitely generated module. It's like for D modules who can have delta functions, which get quasi-coherent shifts. It is not in general coherent. So it's finitely generated. Although the module is holonomic over the big ring, over a small ring it's not. And what one can do? First of all, this module one can decompose into something like torsion. So it means that a vector, such that you apply this operator, you get finite dimensional space. Yeah, so you get torsion plus it contains a torsion, and then you get a quotient. It's not. It doesn't split in canonic as a module, so you get a quotient. It's kind of torsion free. The torsion is it's something very simple. It's, we kind of understand it. We consider kind of orbit by geometric progression, x0, qx0, q square x0, and so on. Something like infinite sum over n over z over Yeah, so now it's doing really global classification, so in a sense we cannot formally use the previous results. It should stay from the thing. It's indecomposable things will be the following things. You consider direct sum of n over z over the following thing. You consider O of maybe some divided by maximal ideal x minus, I just will write explicitly qn x0. You kind of write function up to nth order kind of skyscraper shape at point x0 and maybe raised to some power m. M will be multiplicity. Yeah, so it will be get the Sobius torsion modules. What are torsion-free modules? Torsion-free modules looks like it's a vector bundle. For torsion-free, you get think that if you consider you get a module and maybe call it m prime, then if you consider m prime modulo x for any x0 m prime for any maybe x1 m prime for any x1 is vector space of the same rank. Rank R for any point x1. So you get kind of holomorphic vector bundle, but it's not an algebraic vector bundle, although it's quasi-coherent sheaf. Namely, the typical example is the following: if you consider like quantum modules correspond to the problem something like psi of qx is equal to 1 minus x psi of x, something like this. You consider this Q difference equation and corresponding module. Then this corresponding module is the following. We consider functions in X, I consider Laurent polynomials, but also to Laurent polynomials we add 1 over 1 minus X get infinitely many things. It contains and it's kind of rational functions which allow to have poles at this point, so that with poles of order at least 1 at point x equal to 1, at most 2 at x equal to 1 over q, and so on. So one can kind of informally write this m, it's kind of quasi-coherent sheaf, associated to some infinite divisor, minus, or maybe 1 times 1 plus 2 times 1 over q, something like this. Or maybe I just maybe I start from qx. Yeah, it depends on normalization. Yeah, it's 1 q, 1 over q square. Sorry, I just changed a little bit. Normalization. It will be just different description of the same model. Consider a kind of infinite divisor and consider functions which allow to have poles of order at most 1 here, at most 2 here, at most 3 here, and so on. Yeah, so it's infinite kind of. What? Q? No. Sir? Yeah. Yeah. So that's a typical torsion-free module, but which is not. Yeah. This is kind of torsion game, and if it will be vector bundle, then it will be easy. Yeah. And now let me try to formulate you global meromorphic classification. It's one kind of should use this result by local meromorphic classification and kind of massage with all these effects and see how it all works together. And the answer is extremely neat. Global classification is the following. This holonomic, the category of holonomic AQ modules is equivalent to, I would say what is the category structure? I'll just say the classification first. It's the following. It's coherent sheaf on elliptic curve with two anti-Hadron similar filtrations. Why two filtrations? Imagine that my module is a algebraic vector bundle. And then to understand this vector bundle, we should, first forget about algebraicity. We get vector bundle on elliptic curve by quotient quasi-action. And then the meromorphic structure at 0. But now we have two meromorphic structures because we can approach 0 and approach infinity. Multiply by positive and negative power of q. And each extension by this classification theorem is equivalent to choosing anti-Hadron similar filtration without torsion part. Yeah, so in this case, we get two anti-Hadron filtration without torsion part. And the claim that this complicated intermediate behavior will put also torsion part into the game. And why it's nice? Let's explain the following story. Maybe I'll just make some very general remark. There's a general notion of Bridgeland stability on triangulated categories. If you have triangulated categories, triangulated category, then you get a map from K0 this category to complex numbers. Then Bridgeland stability structure is a choice of some things called collection of full subcategories where theta is a real number, such that for any object in this subcategory, the central charge of the object belongs to exponent I theta times positive numbers. So it's non-zero. It consists of non-zero objects, and for any object f, there exists unique filtration. There are actually maybe two conditions that if theta 1 is bigger than theta 2, then hom of C sigma 1 sigma 2 SS is equal to 0, and also maybe if you shift it by pi, it's the same as shift by 1. Theta by 1, shift by 1 in the sense of triangulated category, and any object has Hadron normal zero filtration in triangulated sense, which is kind of obtained by extension of object in semi-stable things with theta 1 bigger than theta 2 and so on. Consider you can have subobject with some kind of as largest possible theta, then the quotient to get another subobject maps to something which is largest possible theta and so on. Yeah, so it's some kind of very nice notion which is essentially equivalent to making T structure, you get abelian category, and then you get picture with stability like we have before. So it's a general notion, and the claim that this is a kind of construction. If for this triangulated category, you get abelian category, which will be Artinian. And the category can be described like this. You take, you get something like heart of T structure. You get object which build theta maybe goes between 0 and pi in the Hadron similar decomposition. You consider heart of T structure and consider two anti-Hadron similar filtration. And the claim that such things will be object of certain nice abelian category, associated to triangulated category. What is the meaning of this category? Is the following. one can imagine that my category is, let's say, Fukaya category of some Calabi-Yau variety, or something like this, of any dimension. And now I want big tensor product of this Fukaya category with Fukaya category of a torus, two-dimensional torus. Yeah, so it will be again product of two Calabi-Yau categories, but this Calabi-Yau category I consider is very small. It's kind of very, very tiny Calabi-Yau and multiplied by a torus. Now, what is expected in kind of mirror symmetry is that if you have Calabi-Yau variety, then it should have stability structure, and stable object should be special Lagrangian subvarieties. And if you try to think what are special Lagrangian subvariety in the product of your variety and a torus, you get something very, very small, fiber over torus, two-dimensional torus. And now, if you're interested in special Lagrangian, in the product, maybe some variety x, sitting in S1 square times x, but x is small. It's essentially a special Lagrangian variety here and a straight interval in a torus. And what you should get, you get a picture, things like this. You should get a graph, a straight graph. On each vertex, you get, on each edge, you associate a semi-stable object of your fiber category. But for the total slope to be, say, 0, the directions, because at flat torus we can speak about directions because parallel transport is 0. The direction of its edges should be argument of central charges of this object of a torus, yeah, on a fiber. So you get a bunch of objects with different slopes, kind of literally represented by charges like this. And now we should make, if you get something like vertex of degree k vertex, k is at least 3, because it should be kind of hyper balanced condition, then it's equivalent to representation of quiver ak minus 1. Yeah, if we forget, so how this object interact with each other, we consider the following thing. We consider quiver ak minus 1, it has cyclic symmetry, and we make tensor product. So it's, if it's 3, we'll be say that 3 objects form exact triangle, some generalization of exact triangle, exact k-gon. And what we say, we get semi-stable object forming exact polygon, and order given by this order of slopes. Yeah, so it's some kind of pretty general abstract idea which gives this abelian category. Because it will be hard of T structure, for example, consider object of slope 0. Yeah, so you get nice abelian category. No. It's kind of in this picture, kind of global slope is 0. Then it will be said that the direction of the things will be exactly arguments of central charge, not shifted, rotated. Yeah. Let's say here global slope, global argument is 0. So it means that direction of things will cancel the direction of the argument. Now, so it's a pretty general story, and the category will be really Artinian because it will be like things with 0 slope in extra category with stability. So it's some kind of only motivation why this 2 Artin Harder and why 2 Artin Harder Noetherian filtration, because it's essentially you have your object, you decompose things sitting in one domain. It will be from this side you get one filtration, or from this side you get another filtration. If you draw this picture, this will be 2 filtrations of the same object. Because this picture one can draw if you draw the line as 2 filtrations of the same object in plane abelian category. Now, so you get this picture. And what is the corollary of all this general picture? If you start to modify, if you move stability structure, move continuously, stability structure, yeah, essentially by main result in the story, if you just move continuously central charge, then you can move continuously, move your stability structure with it. But we move continuously such that no semi-stable object will appear or disappear. So there will be no wall crossing, nothing. There will be no changes in space of stable objects. And also, you can, for example, part of the story can apply, for example, GL2R universal cover. It acts on the space of stability condition, acting by GL2 plus universal cover. Yeah, so you get this thing. And for case of elliptic curve, it's very nice if you you have the stability structure, but if you apply Fourier-Mukai transform for elliptic curve, you get equivalent under this movement stability structure. So the color that SL2Z without hat, just without acts on this abelian category, on this canonical abelian category associated with dB of coherent shifts on elliptic curve via Fourier-Mukai transforms. Because if you apply SL2Z, you get different stability structure, but you can deform, put it back to original by using GL2R, and this is transformation which doesn't change stable objects. They do not appear and disappear. Yeah, so we get this remarkable huge abelian category in which SL2Z acts via Fourier-Mukai function symmetry. And what is beautiful here, SL2Z also acts by automorphism of category of holonomic model because it acts by automorphisms of the is the same as SL2Z acting by automorphisms of, in fact, maybe of this quantum torus. Yeah, so it's a completely symmetric description, in the kind of compatible with kind of Fourier transforms and whole picture, and yeah, so that's nice result here. I think I maybe stop with analogies. We can maybe remove this big table because I will go further. Yeah, so it looks like pretty satisfactory description, completely analogous to picture for differential operators with complete control of everything, in the sense with there's nothing to add, but there is still something to add, and this is the following. For case of D modules, X is algebraic variety, smooth algebraic variety over C. There was some very remarkable conjecture by Kashiwara and proven by Mochizuki in his volumes. What says this conjecture? What does this conjecture says? Suppose you have complex algebraic variety. Then consider the following. I want to define something like dual to Schwarz space, distributions with polynomial growth. Yeah, so it will be kind of Schwarz space when we multiply by densities, dual, yeah. Schwarz space, it's like functions which have very fast smooth decay infinity. And how we define this Schwarz density dual? We choose any compactification, algebraic compactification of variety, and consider C infinity functions on x bar times density times the absolute value dx, kind of times density, vanishing with all derivatives at infinity. And this space doesn't depend on choice of simplification. You just easily see if you make blow up, it will be the same condition. Yeah, so you get a nice nuclear space. You take dual space. You get, like for X will be affine space, you get space Schwarz space. And this is module over, it's also can make shift on compactification if you're more careful. It's kind of module over both differential operators in X in holomorphic, in anti-holomorphic directions. And then we can, let's assume that X will be maybe affine, it doesn't really matter. Then we can consider for any holonomic dx module, we associate home from dx modules from M to this Schwarz dual thing. And the theorem said that it is holonomic module over complex conjugate variety over dx bar module. And it gives equivalence between dx modules opposite, holonomic dx module opposite, and dx bar modules like this. And correspondence is kind of funny. For example, consider just in one variable, variable x, you consider d modulo x to power lambda, then you want to make kind of distribution, you consider x bar to power lambda, because x bar to power, their product, it's kind of has polynomial growth, it's no ramification. But if you take something like exponent 1 over x bar, then it should multiply by exponent minus 1 over x bar prime, because the product it will be e times 2 times imaginary part of x will be, the product will be things of size 1, it will be nice distribution as well. Yeah, so it's some kind of different game from polynomial and exponential growth. And that's all. Now theorem. Now we want to make something similar for the QD modules. And now what I can assume that Q is right exponent of 2 pi I tau. And now the only assumption which I have now, I don't assume now that it's root of 1, not root of 1, it could be root of 1. Now I assume that tau is not negative number. So it should be, tau could be anything. Could be upper half plane, positive number, or low half plane. If I write like this, I write what is Q prime will be exponent of 2 pi I over tau. Not minus 1 over tau, it's people like in modular form, so I really go from upper half plane to low half plane. I get this things, and this kind of, maybe kind of, let's put it conjecture. And maybe somebody will prove it. Yeah. So the conjecture is that I propose you some bimodule which will identify for certain, for kind of S prime Q difference, which I defined below. The same, if you consider home from AQ, it will be bimodule over AQ cross AQ prime module. It will be bimodule over the thing. Home from AQ for something to this SQ prime. Maybe it gives equivalence. Holonomic AQ model opposite to holonomic AQ prime module. And what is this? What is this thing of these distributions? First of all, we want to start with Engelkov Schwarz function, something with fast decay. And this Schwarz function, the S will be defined the following. It's consider space of holomorphic functions. Yeah, so the key idea here, why I make this modular transform, one can make algebras AQ to quantum torus acts commuting with each other on functions of some sort on variable Z. Yeah, for example, I don't know, unless it's yeah, for example, consider just functions in variable Z and consider operators fz goes to exponent of 2 pi I z fz. Fz goes to fz plus tau. Then you get action of algebra AQ because the product in one direction different with different exponent of tau. But now I consider different things. It's actually I think Fadeev maybe proposes this is the action of AQ prime. And this action commutes with each other. For example, this guy, and this guy commute because you get multiplication by 1. So you get action of two commuting tori, quantum tori. And now I want to say what will be space of n-log of Schwarz space, functions with a very fast decay. So the Schwarz space will be defined in the following way. It will be space of holomorphic entire functions. F, such that if you restrict F to any array, an array should go like this. If you get tau, you get variable tau, this is some special direction. You go exactly this way or this way. Yeah, so that's two rays. There are two rays. One and this, yeah. Or parallel, or any parallel to one of both direction. There are two directions in parallel rays. If I restrict, then it will have exponential decay. Faster than exponential decay. So it should go something like exponent minus of z squared, roughly. Yeah, but it's nuclear space, we said it's faster than any exponent. And the point will be kind of uniform on each interval. But so we get this space and S prime. In fact, and this prime will be dual space. But in fact, it looks that for these equations, one can do something pretty explicit version of hyperfunctions. What will be functionals on the space? S prime maybe contains kind of relevant part. The relevant part will be the following. You consider meromorphic functions. It's S, yeah, and maybe I'll multiply by dz because it should be density. And S prime will be functions. It will be meromorphic functions on C with the following condition, so that they poles. These poles should lie in this some neighborhood of. I have this tau and 1, and I consider some neighborhood, and poles should lie somewhere in this domain between them. And if you go to this direction, it will be grow less than equal than exponent of certain constant times absolute value of z. But constant depend on again on this blue along these blue lines. these things should grow no more than exponentially. So we can multiply by, I think, integrate. And also, what you do with poles, you also should choose a path goes from one direction to another, avoiding poles. You can pair now this function of Schwarz space and dual space. You multiply and integrate over the path. And path you choose up to homotopy, and if you surround pole, you can replay by a small loop. Yeah, so that's essentially a description of what are elements of the dual space. It's such things, and I want now to show you why this conjecture is reasonable, that you get equivalence of categories. So it means that for any quantum modules, you should kind of find canonical module over dual variables of parameters, such that together you arrange the functions to something like here you get module in one variable and complex conjugate variable, and arrange them product to some nice function. So kind of polynomial growth. So it will be a similar story here. Yeah, so there are a couple of examples here. Yeah, for example, we can see the function's exponent f of z is equal to exponent of z square over 2 times 2 pi I over tau. That's a nice function. Then one can try to see that, for example, you get this whatever this thing you can consider as variable x and y hat, x hat, y hat, and x prime hat and y prime hat. Yeah. How they x and my functions. Yeah, y hat, x hat is multiplication by coordinates. Now we go to x logarithmic coordinates, and y hat was shift. Now it became additive shift. Yeah, so we see that f of z, f satisfies the relations if you apply y hat f. So you just add tau. It will be equal to exponent of it will be I x hat f multiplied by something, exponent of by some constant. Yeah, so it satisfies this Q difference equation and y hat and x hat, and similarly it satisfies the same things for dual variables. If you shift z by 1, it will be multiplied by this guy. Yeah, so this is a function. And if you look how this function behaves, if you restrict to any rate, it will grow so, or maybe very fast, or will go to down quadratically. But exactly along this direction, it will stay kind of, will be no exponent of quadratic, it will be exponent of linear direction. But coefficients of the exponent actually will change. If you shift this ray, it will grow faster, but still exponentially. So the constant depends on this transversal coordinate. Yeah, so it's a basic example that this function identifies this constant and this constant. Yeah, so it's kind of, or maybe opposite. So it will be co-identified parameters for this modules over quantum torus. It's one example. And there is another example is Fadeev quantum logarithms. So what is Fadeev quantum logarithm? It's, I will not write a formula, but I just draw the picture. So we get 0, 1. We have shifts by 1 and by tau, yeah? Yeah, right. maybe just let's try to draw it carefully. Like this, but then I want to continue it a little bit other direction. Yeah. So what I draw on a complex plane, on this Z plane, I draw kind of octant of points and octant of kind of black points and white points. Let's say it will be poles and zeros of my function. And I make kind of regularized product, where Strauss product to get this is Faddeev dialogue. It's a function which has zeros and poles at this domain. And then it's easy to see that if you get kind of phi z plus 1 is equal to for example, if you shift a variable by 1 and divide by itself, you get poles only along this whole arithmetic progression, which will be zeros or poles of 1 over exponent minus 1. Yeah, so its function satisfies this equation in one variable and similar plus similar for prime. Yeah, get the same equation if you shift in another direction. And this function, if you look carefully, exactly in this, if you go to the middle dimension, will have kind of exponential growth, but not exponential quadratic. If you shift a little bit, it will start grow and decay very fast. Yeah, so that's a function which identifies this QD module, which 1 plus x plus we had. It's kind of self-dual with respect to this generalization of Cauchy-Vara duality. Yeah, so you have this equivalence of category. For any module, get module over a different guy, and this module goes to itself. Yeah, but if it's more complicated, we don't know what goes on. Yeah, it's essentially two examples which we can study. And what I should say about this? Yeah, so this. This gives you some rise to some new SL2Z action. Namely, yeah, it's so it's kind of transcendental procedure, but it's tempting to make the following definition. Just before going on, I just want to say that something very remarkable here goes on. If tau goes to real line, to positive real line, nothing bad will happen. You get still kind of a discrete set of zeros, so the function is very well defined. It could be a rational number, for example. So the situation where quantum torus is bad, I think it can be kind of situation with quantum torus can be regularized to rational numbers in a certain way. Maybe get some kind of semi-stable coherent shifts on some toric surfaces or stuff like this. Yeah, but yeah, so it was a big advantage that there's no singularities like modular forms has at positive real numbers. Yeah, and it's tempting to make the following definition. What is modular QD module, Q difference module? Namely, it's a following. It's a family of modules depending on parameter tau. That's tau, let's in upper half plane. It's a family of modules which are holonomic modules over A exponent to 2 pi I tau of this of this ring, which depends holomorphically on tau. Yeah, we can consider such things. It depends holomorphically on tau. A kind of very special case of interest, it should be depend algebraically on exponent of 2 pi I tau. Yeah, if you can write the module where Q is kind of parameter and such algebraically, that will give automatically such things. And for such situation, one can ask what is SL to Z, or maybe SL2. Let's see. We say it will be not real number. And for such situation, we can ask what will be this SL to Z invariance. Yeah, so here the story goes a little bit like this. We get opposite category, but then if you go back to original category, we should maybe change tau to minus tau, so we go again back to upper half plane. So we get really equivalence of categories of a whatever exponent 2 pi I tau, and is equivalent to a of exponent of 2 pi minus 2 pi I over tau. It's usual SL to this information. It also is equivalent to a of exponent 2 pi I tau plus 1. So one can generate the whole SL to Z. And one can ask, the whole story will be SL to Z covariant. Yeah. And I think in kind of really this special case, it's kind of really nice notion, which what John Zagier wanted to say, this quantum modular forms or Savets, that seems to be the kind of important object here. And we have essentially no examples here, I have to say. We have examples quantum dialogarithm and the simple rank 1 modules will be the only examples which you can start with. Yeah, it looks at, we don't have much examples. I claim we have a huge number of examples because one can make the following game. Like for usual Weyl algebra, or we can make product of copies, make tensor product of algebras, then apply symplectic integer transformation, make push forwards, and eventually reduce to arbitrary number of generators, like 2 generators. And in this case, I think we get all these things coming from nodes, all this business. Yeah, so it's all built eventually from this dialogarithm and stupid monomial stuff. Yeah, and finally, I think it's a final remark about Fukaya and quantization. Yeah, it's more related to kind of what Jan was talking on his lectures. Is some kind of big conjecture that in very general situation for complex symplectic algebraic varieties, Fukaya category of these varieties should be equivalent to non-perturbative algebraic quantization. We consider holonomic modules and also small part of finite modules of Fukaya category. But Fukaya category consider non-compact property which goes to infinity in some way. And here the picture is the following. If you consider C star cross C star, the quantization should be our torus. But now C star maps to R2 by a logarithm of norms. And this in R2 we draw a finite collection of rational rays. It will be terms of my, when I get this anti-Harlan-Field filtration. And what are really interesting in kind of special, in Lagrangian varieties, which go asymptotically to this race. It could be some curve here, projects essentially something asymptotically goes to this race, and get this part of Fukaya category. And the claim that this part of Fukaya category is equivalent to holonomic modules with given this terms of irregular filtration, these rational numbers. Why? Yeah, so it's so one should kind of explain what is a functor from Fukaya category to whatever IQ modules. And if you try to make the functor, you can do the following. You can just kind of along x variable. I will finish in 2 minutes. You get x variable. You consider object of. You get here maybe my Lagrangian object in Fukaya category. What will be the model? The model will consider a kind of equivariant vector bundle with filtrations. What will be equivariant vector bundle? I consider for any point in C star, and for any maybe mu in C star, I have object of Fouquet category, kind of with transversal to infinity. Yeah, assume that there's no vertical direction here. Transversal to L at infinity. And what is the object? I consider x0 times C star in y direction. It's a Lagrangian subvariety. And put local system of rank 1 with monodromia equal to mu. So I get two-parameter family of objects. Then consider home to this two-parameter family of objects. They are not obtained by Hamiltonian isotopy, so they look like different. But in fact, if I kind of move x0, it will be the same as I multiply mu by opposite number. It's kind of usual story. In Fouquet category, consider non-exact deformation of by closed one form. It's the same as you twist local system. Yeah, so it means that in these parameters x0 and mu, one gets some foliation. Kind of on C star with x0 and mu, you get a foliation along which this object is preserved. So the homes will be preserved. And so you model out by foliation, you get this elliptic curve. Wonderful. You get C star divided by power of elliptic by Q power Z. But the trouble is that you get for parameter tau dual parameter. So one should apply this big duality to this game to back to original quantum torus which you want to expect. Yeah, so it's so the whole things are tied together, and and also the last thing which we expect with so things which we're discussing with Jan for several months, maybe a year, or, about a year, so and this kind of duality should give something like analog of harmonic metrics. You get Keller, hyperkähler structure, and all this business like from Simpson theory from this picture. Okay, thank you.